Okay, let's look at number 4. Number 4 is very like a problem that we've already solved in the notes. We'll go ahead and do it anyways. So the problem says that a manufacturer needs to make a cylindrical can. So we're going to have a cylinder, circle on the top, height, circle on the bottom, that will hold 1.5 liters or 1,500 cubic centimeters of liquid. We don't know what the liquid is, it doesn't matter. Determine the dimensions of the can that will minimize the amount of material used. So we know that we're going to be looking for dimensions. So we're going to have a height and we're going to have a radius. So those are our two final answers that we need to give. And we want to minimize the amount of material. So that's talking about surface area. So here we have volume, and here we have surface area. So we know that volume of a cylinder is pi r squared h. And surface area, we'll call that S. Surface area is all the things that are on the outside of the can. So we have a top and bottom circles. So we have two of those. And the area of a circle is pi r squared. We need to add the area of the sides, which will be a rectangle when you flatten it all out, which is the circumference of a circle times height. So circumference of a circle is 2 pi r times our height. Minimize the amount of material. So that means the area on the outside. So this is what we need to minimize or take the derivative of. This was a number that was given, so this is our constraint. 1,500 is going to be equal to our volume, pi r squared. This is our constraint that helps us give an answer. We need our surface area in one variable. So we're going to use our constraint to help us do that. You can solve for r or h. It does not matter. Usually I choose the one that's easier. In this case, that would be h. Because if you choose r squared, you'd have to take the square root, and then you'd have to take the derivative of that, and it'd be kind of crazy. You can do it, and it would work out. It would just be a little bit harder. So let's solve for h. H is 1,500 divided by pi r squared. So we can take this information and plug it in up here to our surface area. We'll leave 2 pi r squared alone, plus 2 pi r will also leave alone. But height is what we're going to change. So height will become what we found. We found that it was 1,500 divided by pi r squared. This is what we'll take the derivative of. Before that, let's simplify. We have multiplied by pi divided by pi. Those can cancel. We have multiplied by r divided by r squared, so we'll leave one on the bottom. So our new surface area that we'll take the derivative of is 2 pi r squared plus 2 times 1,500 is 3,000 divided by r. This is what we'll take the derivative of. So let's take our derivative. The derivative of s. Remember, 2 pi is a number, so we're really just taking the derivative of r squared. So that's 4 pi r. Then we have 3,000 over r. Remember, when we're taking our derivative, it's easiest to have exponents. So we have 3,000. If we're going to rewrite r, we have an exponent of -1. So to take the derivative, we have 3,000 times -1 is -3,000. Times r squared, negative squared, because -1 minus 1 is -2. So that's what comes in. We have minus 3,000. I'll rewrite this as a fraction because it's easier to see what you need to do and solve when we don't have negative exponents. So we have over r squared. From here, we need to find our critical values. So 0 equals 4 pi r minus 3,000 over r squared. Right now, this would be a little bit difficult to solve for r because r squared is in the bottom. So if you want to get rid of a fraction, multiply by what's on the bottom. That r squared is making the fraction, so we'll multiply by that. 0 times r squared is just 0. 4 pi r times r squared is 4 pi r cubed. R's cancel, that's the whole point of this, and we just have minus 3,000. This we can solve. Add 3,000 equals 4 pi r cubed. So r cubed equals 3,000 over 4 pi. And to get that by itself, we'd need to take the cube root. So we have cube root. You can leave it like this for an FRQ, but remember we are going to have to plug this back in to get our radius if this is our minimum. So when we do that, we get 6.204, 3 decimal places because we're in AP Calculus. Now we can just make sure this is a minimum. We know we don't want any negatives, so the smallest is going to be 0. We're checking 6.204. So let's choose something close to there. Let's choose 7. And let's choose 1. When you plug that into your derivative, when you plug 1 into your derivative, we get a negative. And we're going to cube 7 times 4 times pi. We will indeed get a positive. So this is a minimum. So this is our radius. So to figure out our height, we come back up here. Our height is 1,500, or 15,000, not 15,000, 1,500 times pi times r squared. Our radius is 6.204, and square it, which would be fine for an FRQ, but we already have 1 in a decimal, so let's get the other in a decimal. So this is approximately 12.405. So let's look at the question. What dimensions of the can minimize the amount of material? So let's give our dimensions with units. We need a radius and a height. So our radius is 6.204. Let's look at our units. Our volume that we used is centimeters cubed. So our one-dimensional parts are going to be centimeters. Whoops, fix that on the computer. Okay, centimeters. Oh my goodness. This computer. Okay, centimeters? Yes. And our height is 12.405, same units of measure, centimeters. These are the dimensions that will minimize the use of material to make the can.